What's up, everyone? Welcome back to the channel. Today we are talking about YOLO. No, not the phrase you yell at before making questionable life choices on Friday night. But you only look once. The AI algorithm that completely changed how computers see world. Imagine self-driving cars, security drones, or AI webcams. They all rely on detective stuff instantaneously. Today, we are cracking open how YOLO works under the hood, step by step. Let's jump in. First, let us clear up classic point of confusion. Classification versus object detection. Look at the image on the left. The standard classification is like asking your AI, hey, what is in this photo? And the AI says, golden golden retriever 99% sure, fantastic, good doggo. But if a self-driving car only knows that a pedestrian exists somewhere on the street, that's a disaster waiting to happen. We need to answer two questions at once: what is it and where is it located? The object detection, as seen on the right, it outputs both case, class, label, and exact bounding box coordinates x, y, w, and h. Before YOLO came along, how did computer detect objects? They used two-stage pipelines like RCNN. Imagine trying to read a book, but instead of scanning the page, you take a separate photograph of every single sentence. That's literally what RNN, no, RPN, Regional Proposal Network, did, generating over 200 candidate boxes per image. The result, sure it was accurate, but it crawled along at 5 to 7 frames per second. If you put that in an autonomous car driving at 60 meter per hour, by the time it detects a stop sign, you are already in the next zip code. Let us look at the evolution on this chart. Early models like RCNN and fast RCNN were two-stage algorithm, super slow. Then came single-stage architecture like SSD and YOLO. Single-stage model traded a teeny bit of marginal accuracy of massive reduction in latency. YOLO basically said, forget proposing thousands of individual regions. Let us process the whole image in one single unified pass. Here is a big breakthrough. YOLO reframes object detection from a multi-step search to a single regression problem. You feed an input into a unified neural network and in one single forward pass, boom, it outputs a 3D tensor packed with bounding box coordinates, confidence scores, and class prediction all at once. It literally looks at the entire image exactly once. Okay, so how does it actually do this magic? Step 1. YOLO divides the image into S by S grid, usually 7 by 7 or 13 by 13. Now, write this down because this is a golden rule of YOLO. Whichever grid cell contains the exact center of an object is solely responsible for detecting the object. Even if a sports car spans across 10 grid cells, only the cells containing its center point gets assigned the job. This localized responsibility stops multiple cells from fighting over the same object. Now, what does each grid cell actually calculate? Every single cell outputs a structured vector containing center coordinates xy relative to that cell. Second, width and height wh relative to the whole image. A confidence score, how sure the model is that an object exists inside that box. Class probabilities. Is it a person, a car, or a dog? And all this together, and you get your total prediction vector per cell. uh, what happens when object overlaps or have totally different shapes, like a tall person versus white car? Enter anchor boxes. Think of anchor boxes like predefined cookies cutters. Instead of predicting box shapes from absolute scratch, YOLO predicts teeny mathematical adjustment to these predefined shapes. Anchor 1 handles tall vertical shapes, people. Anchor 2 handles wide horizontal shapes, cars. And Anchor 3 handles squarish shapes. Let's start non-maximum suppression. Because thousands of predictions are happening at once, state A looks like an absolute mess of overlapping boxes around our dog friend here. To fix this, Yellow uses non-maximum suppression (NMS). NMS uses a metric called intersection over union, which is simply area of overlap divided by total area of union. If two boxes overlap significantly, NMS keeps the box with highest confidence score and deletes all the lower confidence duplicates, leaving us with state B, one clean, beautiful box. Decade of evolution. Euro didn't just stop at version 1. We have seen over a decade of continuous upgrades. Yellow 2015, the original single pass revolution, Yellow V2, V3, introduction introduced anchor boxes and multi-scale future pyramids to catch tiny objects. Yellow V5, version 5 to version 8, PyTorch integration and lightweight anchor free hands optimized for edge devices like phones and drones. Yellow version 10, version 11, NMS free training that eliminates post processing bottlenecks together. Here is the cool part of developers. Under the hood, YOLO is a monster. 106 layer deep convolutional network. But thanks to modern Python library like Ultralytics, running inference today literally takes 3 lines of code. Import YOLO, load the model, run results equal to model street skin or jpg and whatsoever, and you are running state of the art vision models in a second. How does it catches object of all sizes? Yellow processes image through a backbone network like darknet across 3 different grid scales. A coarse 13 by 13 grid of large objects, a 26 by 26 grid of medium objects, a fine 52 by 52 grid of small object. Sum it all up and network makes over 10640 prediction per frame in a split second. For you math lovers out there, how does yellow train? Its loss function is combined balance of 3 things. Bounding box losses MSE penalizes inaccurate box location XY and dimension W, H. Objectiveness loss BCE penalizes false positive and false negative is something there or not. Classification loss BCE penalizes predicting the wrong category. Example mistaking a cat or a car. To wrap it all up, YOLO unlocked real-time AI by shifting detection to a single pass regression problem. It unified coordinates and class prediction into one tensor output, enabling 100 FPS, 100 plus FPS performance even on consumer hardware. What's next? Computer vision is moving toward vision transformers, VIT, and 3D neural radiance fields. If you want to run this exact code yourself in Google Cloud, scan QR code on a screen right now and check the GitHub link in the description below. If you found this video helpful, smash the like button, hit the subscribe and leave a comment letting me know what AI model we should break down next. Until the next time, keep coding. Bye.